Happy Earth Day, and welcome to the 10th webinar in our Lunch, Learn, and Dance Wellness webinar series, Radon. My name is Lynn McDonald. Joining me in the chat room is Maria Costa. Kim from Arawaka Latin Dance Company will be leading us in dance beginning at 12:30 Eastern. Let's take a moment to go over the functionality of the Zoom webinar. The audio and video will be from the presenters only. We have found that although you can access the audio through the computer or telephone, the quality of sound tends to be better when listening from a computer. There is a chat feature where people can discuss. If you would like, take a moment now to say hello and where you're from. If you have questions arising from the content, please enter them under the Q&A section. As the webinar is only a half hour in length and is immediately followed by our dance lesson, time may not permit for me to answer them during the webinar. The answers will be posted on our website along with a link to the video recording and a copy of the slides. This can be found under Education Webinars. I will be sending a confirmation of attendance email after the webinar and will include a link to the page with that communication. I will also include the topics covered and the length of time spent in the webinar, as some people have requested this to send to the professional association. Lastly, I have automatic closed captioning enabled in the slide presentation. If they're being blocked by your Zoom controls, you should be able to select a different way to view the webinar in Zoom, which makes them easier to see. In this webinar, we will discuss radon for the general public. First, we'll answer the questions. What is radon? Where is it found? How does it get into our homes? What are the health risks? And how do I measure for it? We'll then give an overview of guidelines for radon in Canada, comparing those for the workplace with those at home. We will then explain what homeowners can do for elevated levels and where to get more information. Information from external organizations is quoted directly or paraphrased from their online resources. Radon is a radioactive gas. It is a noble gas, so it does not chemically react with other substances. It cannot be detected by our human senses. It is colorless and has no taste or smell. Radon occurs naturally from the breakdown of uranium in soils and rock through radioactive decay. It is water soluble. It is about 7.5 times more dense than air, so it will sink in a relatively airtight room and accumulate, similar to how propane gas builds up in an enclosed space from the bottom up. Because radon-222 occurs naturally from the breakdown of uranium in soils and rock, it is found worldwide and in every province and territory in Canada. Levels and areas vary with the type of terrain. Being a gas, radon can move through cracks and spaces in the rocks and soil. It can also hitch a ride with water flowing through rock where it is being created. When radon is released from the soil or rock to outdoor air, it is generally found in low concentrations that we don't need to worry about. However, if radon enters the buildings where we live and work, it can build up to high levels, well above what is naturally found outdoors. Radioactive materials decay in an attempt to make their nucleus stable. They eject alpha or beta particles or emit gamma rays. One property of radioactive substance that can be measured is its activity. Activity is the rate of radioactive decay. In other words, the number of radioactive decays which occur in a moment of time. A becquerel is 1 radioactive decay per second. Another important property of radioactive material is the half-life. The half-life is an indication of how long a substance remains radioactive. Specifically, it is the time required for half of the radioactive atoms in a material to have decayed or emitted radiation. After 1 half-life, the activity will have decreased by 50%. After 2 half-lives, it will be down to a half of the original activity, or 25%. This will continue until the material is basically no longer radioactive. The half-life is a quantity which is unalterable. It does not matter whether it is chemically bonded to other atoms or not, or whether it is a solid, liquid, or gas. You can heat up, cool down, or change the pressure of radon gas, and it will still have the same half-life. There are well-known naturally occurring decay series, one of which is the uranium decay series. Radon-222, the most stable isotope of radon with a half-life of 3.5 or 3.8 days, is part of the uranium decay chain. The shorter-lived isotopes of radon do not get as much time to travel in the soil and water, and therefore do not tend to build up in confined spaces in the same way. Progeny or daughters are the material that remains after a radioactive decay occurs. Radon progeny are radioactive as well. For health effects, only the short-lived progeny are considered. Radon progeny are solids and can attach to aerosols and dust particles in the environment. When inhaled, these tend to remain in the lungs, whereas the radon itself you can exhale. Polonium-218 and polonium-214 are of particular concern as they are high-energy alpha emitters with relevant half-lives. While alpha particles cannot penetrate our dead layer of outer skin because they deposit their energy over very short distances, they are very damaging to living tissue when being emitted inside the body. There will be no immediate symptoms, but exposure increases the chance of a mutation, which in turn leads to an increased risk of developing lung cancer. Radon can enter into our homes and buildings in various ways. Firstly, it enters where the building is in contact with the soil, through cracks in the subslabs or walls that are in contact with soil, gaps at floor wall joints, through porous concrete block walls, open sump pits, through floor drains with no traps, openings in the foundation around utility penetrations, and utility tunnels in large buildings. There are also small amounts of radon which are attributed to the production and use of natural gas. Radon can also enter from emission from water, particularly ground or well water. Radon can dissolve and accumulate in water from these underground sources when it passes through rocks and soil containing some uranium. This dissolved radon can escape from the water into the air. Radon will transfer from still water to air, but this usually takes hours. More radon escapes from water into the air when it's agitated, for example, through splashing, spraying, boiling, etc. The ease of radon transfer to air depends on the temperature of the water, the temperature of the air, and the degree of agitation. In a typical dwelling, water with 100 becquerel per liter of radon results in an additional 10 becquerel per cubic meter of radon in household air. These physical processes can remove a lot, but some radon stays in the water, which can then be ingested. That being said, the inhalation of radon and radon progeny is of a greater health concern than the ingestion of dissolved radon in water. Being exposed to high levels of radon gas is the second leading cause of lung cancer in Canada after smoking. According to the Canadian Cancer Society, 1,700 new cancer cases per year are due to exposure of high levels of radon gas. Lung cancer due to radon exposure is a stochastic effect, which means it is not a certainty. This is because development of lung cancer is probabilistic and not deterministic. Not everyone exposed to elevated levels of radon will develop lung cancer. There is no lower threshold below which the exposure presents no risk. The risk of getting lung cancer from radon depends on how much radon is in your workplace and home, the occupancy time in these areas, the age of exposure, and whether you're a smoker or have ever smoked, as smoking and exposure to radon are synergistic. This means that the combined effect of smoking and being exposed to high levels of radon gas have a more drastic effect than adding the expected results of the two factors together. Radiation dose is measured in a few different ways. One unit of measure for doses of radiation received over a long period of time is a sievert. The risk of developing a fatal cancer as a result of exposure to radiation over a long period of time is approximately 4% per 1,000 millisievert. In Canada, approximately 25% of people develop a fatal cancer in their life. So the risk of developing a fatal cancer to a person who received a 1,000 millisievert dose of radiation over a long period of time becomes 29% instead of 25%. This means in a population of 100 people who were exposed to no extra radiation than a typical person, compared to a population where everyone received an extra 1,000 millisievert dose, there would be 29 people who have a fatal cancer rather than 25. For more information on radiation activity and dose, please see our webinars, Understanding Radiation and health effects of exposure to radiation. Because people do not possess any sense organs that can detect radiation from radon and its progeny, we must rely entirely on instruments to detect and measure them. Radon progeny cause the most dose, but due to their very short half-lives, they can be difficult to measure. Generally, radon gas concentration is measured instead because it's much easier to detect. To convert to a dose, an assumption is made about the relative concentration of radon progeny to radon gas, called an equilibrium factor. Radon gas concentrations can be measured in many ways, including short-term and long-term measurements. Short-term devices include grab sample and charcoal canisters. Long-term devices include the electric monitor or EPERM and alpha tract monitors. Continuous electronic monitors are also available. Short-term monitors obtain a sample of radon at a particular moment in time. They may or may not require a power source. They must be sent away for analysis at a laboratory. Some types of these tests, such as charcoal canisters, actually capture radon, and that is what is sent in for analysis. But the radon is decaying as you send it. If it takes a week for it to get to the lab, only a quarter of the radon is left in the container compared to what was there when the sample was shipped. So the time in transit is important. Although they are relatively inexpensive, these types of monitors are not a good indication of long-term average concentration because they're only measuring for a few days. As such, they are not recommended by Health Canada. Why is it important to get a long-term average of radon concentrations and not a short-term measure? Radon concentration in buildings is affected by the uranium concentration in soil and building materials, soil characteristics such as permeability and compaction, radon concentration in water and amount of water being used indoors, the heating, ventilation, and air conditioning system in the building, environmental conditions such as temperature, barometric pressure, precipitation, humidity, and wind speed, and occupancy patterns, including how often doors and windows are opened and closed. Because radon concentration depends on so many factors and is variable not only over the day-to-day, but by season, you might be measuring in a low time or a high peak. This means they don't give a good indication of a long-term average concentration, which is what we're interested in. Think of it as being like measuring temperature. If I measure temperature at 4 in the morning one time, it's not a good indication of the average temperature over the week. It will be lower than average. Similarly, if I measure temperature at 5 in the afternoon, it will be higher than average. Long-term monitors gather data for 3 to 12 months. They usually don't require power. They are also sent away for analysis at the laboratory, but due to their construction, they do not lose information during normal transit. They give a much better indication of long-term average concentration and are also relatively inexpensive. As such, Health Canada recommends that people use long-term monitors. For best results, use them during the heating season, as this is when most people keep their doors and windows closed and do fewer exchanges of indoor air with outside air. They should also be placed in the lowest occupied level of the residence. Alpha tract detectors are typically a plastic housing with a filter-covered opening that allows radon gas into a chamber, but not dust or progeny. In the chamber, there's a film or plastic that is sensitive to alpha radiation. Radon gas decays within the chamber and gives off alpha particles. The alpha particles contact the film or plastic and cause damage called alpha tracts. Before returning the test, the chamber is closed. At the laboratory, the detector film is etched to make the damaged tracts bigger. Tracts are counted under a microscope. The number of tracts per unit area proportional to the radon concentration and exposure time. An electric detector is similar in construction in that it is usually also has a plastic housing with a filtered covered opening that allows radon gas into the chamber, but not dust or progeny. The difference is that inside the chamber is an electrically charged metal plate. Its charge is measured before deployment. Radon gas decays within the chamber and gives off alpha particles. When the positively charged alpha particles contact the plate, it lowers the electric charge. Before sending back to the lab, the chamber is closed. At the laboratory, the remaining electric charge is measured. The depletion in charge is proportional to the radon concentration and exposure time. This method is sensitive to gamma radiation, so a correction for gamma background must be made. Continuous electronic monitors generally use ion chamber technology to give real-time readout. Radon enters the ion chamber, and when it decays, the alpha particles cause ionization in the air, which is converted to an electronic signal. Electronic monitors require a continuous power supply. If using, you must ensure to collect regular data over a long period to be able to calculate the long-term average concentration. They are excellent for observing concentration changes over the course of a day or other period, a week, a month, a season, etc., so long as the data is properly gathered. Electronic monitors can be quite expensive, and you must send them away for annual calibration. Health Canada publishes the Canadian Guidelines for the Management of Naturally Occurring Radioactive Materials, or the Canadian Norm Guidelines. These were developed by the Canadian Norm Working Group of the Federal Provincial Territorial Radiation Protection Committee. The basic principle of these guidelines is that the same radiation exposure criteria should be applied where workers or the public are exposed to new sources or modes of radiation from activities involving norm, as for the radiation exposure from the Canadian Nuclear Safety Committee regulated activities. This applies to cases where norm is in its natural state and to cases in which the concentration of norm material has been increased by processing. In the guidelines, you will find dose conversion factors based on measured radon or radon progeny concentration and classifications of workers based on radon concentrations and actions to be taken for worker protection. The amount of radon gas is measured as an activity concentration, or becquerel per meters cubed. According to the norm guidelines, an exposure of 200 becquerel per meter cubed for 2,000 hours results in a 1.4 millisievert of effective dose. Radon progeny is traditionally measured in working levels. Being exposed to one working level for 170 hours results in a 1 working level month exposure, equivalent to 5 millisieverts of effective dose. Remember that 1,000 millisieverts dose is attributed to a 4% increase in the risk of developing a fatal cancer in one's lifetime. The health risk from ingesting radon-contaminated drinking water is considered negligible. The majority of radon escapes into the air when water is agitated, leaving only minimal amounts in the water itself. However, radon in water can significantly increase airborne radon. Canada currently has no guidelines for radon concentrations in drinking water. There are no Canadian federal regulations that govern radon levels in dwellings, although it is included in some provincial or territorial building codes. Health Canada norm guidelines state that remedial measures should be taken in a dwelling whenever the average annual radon concentration exceeds 200 becquerels per meter cube in the normal occupancy area. The higher the radon concentration, the sooner remedial measures should be undertaken. If greater than 600 becquerel per meter cube, remediate within 1 year. If between 200 to 600 becquerel per meter cubed, remediate within 2 years. Remedial action should aim to reduce radon to a value as low as practical. The construction of new dwellings should employ techniques that will minimize radon entry and facilitate post-construction radon removal. Federal regulations apply to federally regulated workplaces and workplaces regulated under the Nuclear Safety and Control Act, including uranium mines, nuclear power, radiation sources, etc. These radiation protection regulations require dose from radon to be monitored and reported. Provincial or territorial regulation applies to all other workplaces in a province or territory. Radon would typically appear in such places as the Occupational Health and Safety Regulations or Mine Safety Regulations. The Canadian norm guidelines recommend all workplaces be assessed for radon concentrations since it can vary significantly. The document provides occupational dose limits for exposures to radon in workplaces that are not uranium mines based on worker type, including occupationally exposed workers, incidentally exposed workers, and members of the public. Limits are consistent with the International Commission on Radiation Protection, or ICRP, recommendations. One example of workplace monitoring are radon progeny dosimeters for miners. These are mandated for use in uranium mines. The Radiation Safety Institute of Canada provides this independent service in Canada with alpha Tract dosimeters shown. This type of dosimeter measures the total exposure to radon progeny over a time interval. Dose can be calculated from the exposure. For formal records for doses above a certain value, generally 5 millisieverts, the dosimetry service provider must be licensed with the CNSC. Now that we've considered what radon is, its health effects, and guidelines for exposure, there's an important question remaining. If you do have high levels of radon, what does a homeowner or landlord do to mitigate it? The first step is to attempt to prevent radon entry into the building, as you would for any soil gas. This requires the homeowner or a contractor to find and seal all entry points, such as cracks, gaps, sump pits, utility penetrations, etc. New home builds can use soil gas barriers between the foundation and the soil to prevent entry of radon and other soil gases. The next level is to maintain positive air pressure versus the soil gas pressure. This is provided by using a specialized fan which puts air into the area where the gas enters, where the foundation is in contact with the soil. If these are not enough, further mitigation can be in the form of subslab depressurization. This involves continuously removing the air from under the slab. The radon is removed before it can enter the building. Some new home builders will install a rough-in for radon subslab depressurization system, saving money for the homeowner should it be needed in the future. To summarize, radon is a radioactive gas that enters homes. Being exposed to high levels of it for a long period of time increases the risk of lung cancer. The only way to know the level of radon in a workplace or a home is to test for it. Long-term tests of 3 to 12 months are recommended. Short-term tests are useful to determine how successful a remediation has been. Workplaces must attain the average annual concentration to compare to the Canadian norm guidelines. If a 3-month test is performed in a dwelling, Health Canada recommends performing the test during the heating season. If there's a high level of radon buildup, remediation measures should be taken. For more information about radon, its health effects, its mitigation, there are several Canadian resources. In addition to the Canadian norm guidelines, Health Canada has information for various audiences available on their website, including the Guide for Radon Measurements in Residential Dwellings. In 2012, they published the results of the Cross Canada Survey of Radon Concentrations in Homes. Over 2 years, approximately 18,000 radon test kits were mailed out to homes across the country. When analyzed, the range of results were from 0 in Nunavut to levels over 23% for New Brunswick and Manitoba. It was found that approximately 7% of homes in Canada have radon levels above 200 becquerel per meter cube, and approximately 0.7% had levels over 600 becquerel per meter cube. These are a representative sample across the country, but please remember that the only way to know whether you have high level rate of radon gas is to test for it. Health Canada has also worked with the National Research Council of Canada, or NRC, to study different aspects of radon gas, including the effects of different mitigation measures on the radon concentration in buildings. The NRC has a research facility called the Canadian Centre for Housing Technology, where model homes are outfitted with various residential products to test their efficacy. The Canadian Association of Radon Scientists and Technologists is an organization with the goal to protect Canadians from radon exposure by providing opportunities for liaison on matters related to radon gas between professionals and other interested public and private organizations, and promoting public awareness and education of radon gas measurement, the health effects of radon gas, and the abatement, mitigation, and reduction of radon gas. They also oversee the CNRPP program, which promotes quality professional standards for the measurement and mitigation of radon gas and provides opportunities for gathering, organizing, storing, sharing, and disseminating information and knowledge related to radon gas, the health effects of radon gas, and its mitigation. While the Radiation Safety Institute of Canada does not recommend individual contractors for detection or mitigation, asking if they're a member of KARST would be a good first step to ensure you're working with an informed professional. The KARST website also provides links to member companies which sell home test kits or provide testing or remediation services. Another venue for finding information on radon, testing, and mitigation is takeactiononradon.ca. It is a national initiative funded by Health Canada to bring together radon stakeholders and raise awareness on radon across Canada. The current advisory team is made up of the Canadian Association of Radon Scientists and Technologists, CAREX Canada, and the Canadian Cancer Society. For a more global perspective, in addition to local government organizations, the World Health Organization, the IAEA, and the ICRP are a good place to start. We hope you have enjoyed this overview of radon gas. If you have any further questions about radon, we have more information on this and other radiation safety topics on our website, which is found at www.radiationsafety.ca. You can also contact us toll-free at 1-800-263-5803 or by email at info@radiationsafety.ca or find us on Facebook.
To register, go to www.radiationsafety.ca/services/webinars.